Good day everyone, this is Prince Rabino and this is the report that I just want to report. The density-based clustering. What is density-based clustering? Density-based clustering refers to unsupervised machine learning methods that identify distinctive clusters in the data. Based on the idea that a cluster group in a data space is a contiguous regions of high point density, separated from other clusters by sparse regions. The data points in the separating sparse regions are typically considered noise outliers. Cluster analysis is an important problem in data analysis. The data scientists use clustering to define malfunctioning servers, group genes with similar expression patterns, identify anomalies and biochemical images, and perform various other applications. There are many families of data clustering algorithms, and you may be familiar with the most popular ones, K-means and DBASECAN. K-means determines k-centroids, the center of a data cluster in the data and clusters points by assigning them to the R centroid. So we have a clustering application k-means. In the above dataset, we run k-means with two clusters. The big blue dots represents the centroid for the black clusters, and the big gold dot represents the centroid for the white cluster. DBSCAN, density-based spatial clustering of application with noise, is the most well-known density-based clustering algorithm. First introduced in 1966 by Esther et al. Due to its importance in both theory and applications, this algorithm is one of three algorithms awarded the Test of Time Award at the KDD conference in 2024. 2014. In this video, we are covering the DBSCAN, which is the density-based spatial clustering of application with noise.
Get started. Most of the traditional clustering techniques, such as k-means, hierarchical, and fuzzy clustering, can be used to group data in an unsupervised way. However, when applied to tasks with arbitrary shaped clusters or clusters within clusters, traditional techniques might not be able to achieve good results. That is, elements in the same cluster might not share enough similarity, or the performance may be poor. Additionally, while partitioning-based algorithms, such as k-means, may be easy to understand and implement in practice, the algorithm has no notion of outliers. That is, all points are assigned to a cluster even if they do not belong in any. In the domain of anomaly detection, this causes problems, as anomalous points will be assigned to the same cluster as normal data points. The anomalous points pull the cluster centroid towards them, making it harder to classify them as anomalous points. In contrast, density-based clustering locates regions of high density that are separated from one another by regions of low density. Density in this context is defined as the number of points within a specified radius. A specific and very popular type of density-based clustering is DBSCAN. DBSCAN is particularly effective for tasks like class identification on a spatial context. The wonderful attribute of the DBSCAN algorithm is that it can find out any arbitrary shaped cluster without getting affected by noise. For example, this map shows the location of weather stations in Canada. dbScan can be used here to find the group of stations which show the same weather condition. As you can see, it not only finds different arbitrary shaped clusters, it can find the denser part of data-centered samples by ignoring less dense areas or noises. Now, let's look at this clustering algorithm to see how it works. dbScan stands for Density-Based Spatial Clustering of Applications with Noise. This technique is one of the most common clustering algorithms, which works based on density of object. dbScan works on the idea that if a particular point belongs to a cluster, it should be near to lots of other points in that cluster. It works based on two parameters, radius and minimum points. R determines a specified radius that, if it includes enough points within it, we call it a dense area. M determines the minimum number of data points we want in a neighborhood to define a cluster. Let's define radius as 2 units. For the sake of simplicity, assume it as radius of 2 centimeters around a point of interest. Also, let's set the minimum point, or M, to be 6 points, including the point of interest. To see how dbScan works, we have to determine the type of points. Each point in our data set can be either a core, border, or outlier point. Don't worry, I'll explain what these points are in a moment. But the whole idea behind the dbScan algorithm is to visit each point and find its type first. Then we group points as clusters based on their types. Let's pick a point randomly. First, we check to see whether it's a core data point. So, what is a core point? A data point is a core point if, within our neighborhood of the point, there are at least m points. For example, as there are 6 points in the 2 centimeter neighbor of the red point, we mark this point as a core point. Okay, what happens if it's not a core point? Let's look at another point. Is this point a core point? No. As you can see, there are only 5 points in this neighborhood, including the yellow point. So what kind of point is this one? In fact, it is a border point. What is a border point? A data point is a border point if A, its neighborhood contains less than m data points, or B, it is reachable from some core point. Here, reachability means it is within our distance from a core point. It means that even though the yellow point is within the 2 centimeter neighborhood of the red point, it is not by itself a core point because it does not have at least 6 points in its neighborhood. We continue with the next point. As you can see, it is also a core point. And all points around it which are not core points are border points. Next core point, and next core point. Let's pick this point. You can see it is not a core point, nor is it a border point. So we label it as an outlier. What is an outlier? An outlier is a point that is not a core point and also is not close enough to be reachable from a core point. We continue and visit all the points in the dataset and label them as either core, border, or outlier. The next step is to connect well. Let's review this one more time to see why dbScan is cool. dbScan can find arbitrarily shaped clusters. It can even find a cluster completely surrounded by a different cluster. dbScan has a notion of noise and is robust to outliers. On top of that, dbScan makes it very practical for use in many real-world problems because it does not require one to specify the number of clusters, such as k in k-means. This concludes this video. Thanks.